Hi. In the video about modeling GDP using first order differential equation, we were trying to find the time path from this differential equation. And in order to do it, we needed to go through enormous effort associated with using integration by parts to find the solution. But as I mentioned this to you during this video, there is a method that kind of allows us to go around this problem. And this method is called method of undetermined coefficients. And this is the method we're going to learn how to use right now on this particular example. Okay, so look, what we have over here is actually a first order differential equation with constant coefficient and variable term. Right? So, this is type of a hybrid of the case where we had just constant coefficient and constant term, which is extremely easy to find the solution, and the case where we have variable coefficient and variable term, well, finding a solution might be a little bit more problematic. So, look, we're going to now solve this equation in the simplest possible way. First, let's remember first fact. What is a complementary function? Complementary function is nothing more than a solution to a homogeneous version of an equation, right? So in this case, all I need to do is to find a solution to this. But solution to this is straightforward, right? Because it actually comes from the formula that we already derived. So this is some a times e to the power negative at. So look, now we already have a complementary function. We don't need to look for it. We know how its specific form, and we know how it works, right? But of course, we remember that yt, so time path of y, is composed out of complementary function and particular integral. And particular integral, in this case, is something that we cannot solve in such an easy way. So, previously, we turned to the formula for the first order differential equation with variable coefficient and variable term, but this led us to a very complicated process of using integration by parts to get the solution. And actually, when we look at this equation, we can figure out easier way to do it. Because look, let's think for a second what actually we do have here. Look, we know that y times some coefficient plus y and dy dt, so function and the derivative of this function are equal to this. So look, let's think for a second. What function plus its derivative, of course with some coefficient, will give us an expression let's call it ct plus d, right? In general. Look, this case we can have only in case of linear function. Why? Because look, in this particular case, we might have a situation when we differentiate y, right? We are getting some constant. And if we are adding them up together, right, we will have just an expression with c plus some constant d, right? So this expression over here will be associated with the linear function. On the other hand, this expression over here is going to be associated only with a constant. So, if this is the case, why not to try it over here? Okay, so look, now I can simply assume that y is going to be beta t plus alpha. And look, right away we get from this that dy dt must be equal to beta. And look, now what have we assumed over here? That this is the full function, right? This is its derivative. So why not now substitute this over here? Okay, so instead of d, so let me repeat the equation. And look, instead of dy dt, we can write beta. Now, instead of y, we can write beta t plus alpha, right? And this is equal to beta 2t plus beta 1. And look, now our entire task is simply to calculate value of beta and alpha and express them in terms of a, beta 2 and beta 1. Okay, to make things simpler, let's first calculate everything out over here. So we get that this is beta plus a beta t plus a times alpha equals to beta 2t plus beta 1. Or if we organize this a little bit to a little bit nicer expression, we get that this is a beta t plus a alpha plus beta equals to beta 2t plus beta 1. Okay, now we will see why do we call this method of undetermined coefficients. Because look, all we're actually going to do is to establish the value of the coefficients we've got here. Look, we clearly see that this expression and this expression are exhibiting some very common features. What are those features? Well, t is in the first power in both of these expressions. So look, the only thing we need to now compare are those two. Because look, out of those two, over here, I'm going to get that a beta t is equal to beta 2t. Well, clearly, the t's are canceling each other out. And right away, out of this, I'm getting the beta is equal to beta 2 over a. And now, we've established our first part of the particular integral in our solution. Okay, now, of course, all we've got to do is to repeat exactly the same thing, but now for constant terms. Okay, so what are we getting out of this? That a alpha plus beta is equal to beta 1. But now, we already established how much is beta equal to. So we've got that a alpha is equal to beta 1. I'm moving it to the other hand side of the equation. And now I'm substituting over here. This is beta 2 over a. And now look, the only thing left we've got is to divide both sides by a, and we get that alpha is equal to beta 1 over a minus beta 2 divided by a squared. And look, this is exactly the same solution we've got using the procedure associated with integration by parts, but of course it took us way much more time. Okay, so now that we know that yp is equal to beta t plus alpha, or in terms of our previous equation, it is beta 2 at plus beta 1 over a minus beta 2 over a squared. Okay, because this is a very complex expression, well, maybe not very complex, but it would be inconvenient. Now when I'm going to make the time path by adding a complementary function and particular integral, I'm going to use this expression for particular integral. So we've got that this is a e to the power negative at plus beta t plus alpha. Okay, and look, of course, this is what we call general solution. How can we get definite solution in this case? Well, not a problem. We will do it exactly the same way as we did before. So, definite solution is simply y0 minus beta t minus alpha e to the power negative at plus beta t plus alpha. Okay, and this expression for definite solution might give us a little bit more hints into how can we use this differential equation to model, for example, GDP, right? Okay, so as before, we are assuming that y represents GDP, real GDP, and I know we did this previously, but let's remind ourselves and introduce a couple of new details into what we've learned. Okay, so here we've got time, and here we've got y of t. And look, first we start with our moving equilibrium. Remember this type of equilibrium, because this is particular integral, so it represents equilibrium, we called moving equilibrium. Why moving? Because it changes with time. Okay, and how should I draw it? Well, it starts at alpha, and it increases with the slope beta over here. And actually, we can read it. We can read it from our, because look, if yp, let's do it like this, is b t plus alpha, then dyp d t is of course beta. So look, we see that of course as time progresses our moving equilibrium increases by beta. So slope of this line is beta. So we've got here beta t plus alpha. And look, if nothing happens, we are going to remain in this equilibrium. But if, for example, at some time y0, we are having some shock. Okay, now let's read it from now let's read it from this expression that we've got over here. Okay, let's just say that now GDP at some time t0 is, let's just say, at this point. So we call it y0. Okay, and what do we see? What do we see from here? That look, actually, over here we've got value of y0, right? Now, if I'm gonna subtract from this beta, okay, let's make it like, oh, I'm sorry, let's make it like this. Maybe this is going to be more better over here. What do we have over here? This is some positive value, but and this positive value is over here, right? Here, I have a beta t0 plus alpha, right? So look, what if I'm going to take this expression, y of t0, and I'm going to subtract this expression, what we see over here, what am I going to get is this distance, but with negative sign, right? Because this is where we should be if we were not thrown out of the equilibrium. This is where we are actually. And look, what is going to happen then? Of course, assuming that A is positive, which we did, we will be moving closer and closer and closer, but we will be moving closer and closer and closer, of course, to the new moving equilibrium. And look, of course, here we see that we have negative shock. So, value of A is negative. Now, if we would have, on the other hand, positive shock, let's just say somewhere over here, but this would be, let's just say some T1, and at T1, the value here is B, T1 plus alpha, and over here, Y, T1. And again, now we see that we are actually above the line. And look, this expression then is positive, but still, assuming that A is negative, we will see convergence to the moving equilibrium. Okay, so this is it about this subject. Thank you for your attention, and see you in the next video.